The second case to consider is when q of x has a product of linear factors, some of which are repeated. And so what that means is that we have a factor that has a power on it, a linear factor in particular. So let's suppose that we have a factor of the form ax plus b, so a linear factor that has a power of r. So in other words, it's repeated r times. So then our partial fractions must contain the following terms: a1 over ax plus b, a2 over ax plus b squared, so on all the way, so building up to the power of r. So ar over ax plus b to the r. So we'll have r constants to solve for, where r is the power. Okay, so let's try this out with an example. Here, let's just start by practicing writing the form of our partial fractions. Notice that we have two linear factors. We've got x squared, but because it has a power of 2, it's being repeated. And then we have this factor x minus 1 that has a power of 3, so that one's repeated as well. This one's got a power of 2, so it'll have, its partial fractions will have a over x and b over x squared. So one for each coming up to the power of 2. Then this one has an x minus 1, and then we'll build up to the power of 3. So we'll have c over x minus 1, b over x minus 1 squared. And then one more. Oh, I'm sorry, that should be a d, right? So it's a different letter. And then one more, so we'll have e over x minus 1 cubed. Okay. So you see there would be actually 5 constants that you would need to solve for in this case. Let's practice this with an example like this. So here we've got x to the 4th minus 2x squared plus 4x plus 1 all over x cubed minus x squared minus x plus 1. Now the first thing that I notice is that this is improper. So we need to do long division. Okay, so before we can do our partial fractions, we need to reduce this into a form where it contains a proper rational function. So let's work out the long division now. So we'll do x to the 4th, make a little space there, minus 2x squared plus 4x plus 1 is divided by this x cubed minus x squared minus x plus 1. So again, we'll start with dividing the first term here, x to the 4th divided by x cubed, which is x. And then I multiply x times our divisor here, so it'll be x to the 4th minus x cubed minus x squared plus x. And then we subtract from above. So x to the 4th minus x to the 4th are gone. 0 minus negative x cubed, so that'll be plus x cubed. Negative 2x squared minus negative x squared, so plus x squared, so that'll be minus x squared. Then we got 4x minus x will be 3x. And then 1 will drop down, we'll bring that down. Okay, and then notice I can do it one more time here because we could do x cubed divided by x cubed is 1. And then I'll multiply each term by 1 here. So of course that just gives me the same thing back. And then I subtract by 1, or subtract from above. So I got x cubed minus x cubed. Those are gone. Negative x squared minus negative x squared, so those terms are gone also. 3x minus negative x, so that'll be 3x plus x, gives us 4x. And then let's see, 1 minus 1. So those terms are also gone. So I'm just left with this remainder of 4x. Okay, so therefore here, let's look at what we have now. So after performing the long division, our integral now will have this polynomial part x plus 1 plus the remainder, which was 4x, over the divisor, which was x cubed minus x squared minus x plus 1. Okay. Now that this is a proper rational function, we can continue with performing partial fractions on just this piece here. So of course, before we get to that, we need to factor that denominator. So actually what I'll do now is I'll just integrate these first two terms, since those are easy to integrate. And now we can just focus on this integral here. So again, I'm going to have to be a little bit tricky about how to factor this guy. I notice that because it's a cubic polynomial, I don't have a nice easy method for factoring it. But if I'm tricky, what I notice is that you can do a little bit of factor by grouping here. So hopefully that's a familiar method to you, but let's group the terms. So I'm going to group these first two terms and group these second two terms. And then I factor out what's common between them. So if I factor out an x squared from those first two terms, I'm left with an x minus 1. And if I factor out a negative 1 from the second two terms, I'm left with an x minus 1 as well. Okay, so then I notice this common factor of x minus 1 remains. And then I can factor out that, and then I'm left with x squared minus 1, which then is a difference of squares, so I know how that factors as well. So that's x minus 1 times x minus 1 x plus 1. In fact, there we see there's two factors of x minus 1. So we have x minus 1 squared times x plus 1. Okay, so all that factoring now we get our integral now has one repeated factor and one distinct factor that's not repeated. Okay, so because this one's repeated, we'll have to use the method that we've described previously. So for the repeated one, we'll have a over x minus 1 plus b over x minus 1 squared, one for each coming up to the power of 2. And then this one's not repeated, so this will just be c over x plus 1. Okay, so we'll have to figure out what a, b, and c are now. Okay, so continuing with the process now of finding the partial fractions, we can use the work that we did previously to get our integral now that we're looking to compute is going to require us to find these three constants, a, b, and c. So let's do the partial fractions to solve those constants. So let's work it out over here. Got 4x over x minus 1 squared x plus 1 has the partial fractions a over x minus 1 plus b over x minus 1 squared plus c over x plus 1. I'll clear out the denominators like we did before, the same algebraic maneuver. I'm going to multiply these two factors, x minus 1 squared times x plus 1, to both sides of the equation. Okay, and doing so here, when I have these factors multiplied by the first term, a over x minus 1, notice that one of the x minus 1 factors cancel, but one still remains. Here, the x minus 1 squared factor cancels, so I'm just left with b times x plus 1. And here the x plus 1 factor cancels, so I'm left with c times x minus 1 squared. Now, to do it in a different way than we did in the previous example, I'm going to demonstrate how we can solve for a, b, and c by expanding out all the expressions here on the right-hand side. So in other words, we're going to FOIL everything completely. Then we're going to combine the like terms so that we can try and match the coefficients on the left and the right-hand side of the equation. So what does that look like? Well, we've got to do a little bit of algebra here to expand everything out. So we got a times, when we FOIL this out, becomes x squared minus 1. bx plus b here when I distribute the b. c times, when I FOIL this out, x squared minus 2x plus 1. Okay, and then I'll continue more distributing here. So we got ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Okay, so everything's been distributed out. Now our goal will be to collect the like terms. So for instance here we've got the ax squared plus cx squared. We can combine those together as a plus c x squared. Okay, next I'll combine the x terms. So here we've got bx and minus 2cx. So I'll combine those together. So b minus 2cx. And then finally we've got the constant terms. So here we've got minus a plus b plus c. Okay. And what I want to do is really compare these with what we see on the left-hand side. So for instance, what I really notice is that on the left-hand side, the coefficient of x squared must be 0. There's no x squared term here. And then the constant term must also be 0, but the coefficient of x has to be 4. So we're going to match them up here. So the constant term here is 0, so that means that this term here must be 0. Right, so that 0 here must match the constant term here. So with that we got one equation, negative a plus b plus c equals 0. The next thing I'll do is I'll match up the 4 here has to match the x coefficient here. So we have another equation there, b minus 2c has to equal to 4. And then same thing here, I'm going to match up the 0x squared term with the coefficient of x squared here, which is a plus c. So that gives me one more equation that a plus c must equal to 0. So now it's like I have this system of equations, and we just need to solve the system to get a, b, and c. Okay, well, one thing I can notice is I could try and eliminate some of the variables. So, for instance, if I combine equation 1 and equation 3, the top and the bottom equation together, if I combine those together, just by adding them, we get negative a plus a, those terms go. Then I got b plus c, so b plus 2c equals 0. Now I can combine that with the b minus 2c that we have here. Because if I combine these together, something else happens, the c's eliminate. So I get 2b equals 4, which gives me b equals 2. Now let's go back and find c. So now that I know b equals 2, then I can put that here. 2 plus 2c equals 0. So 2c equals negative 2, so c equals negative 1. So I've got b and I've got c, so I can go back to either of these other two equations to get a. So maybe it's easiest to go here So if I know that c is -1, then we got a minus 1 equals 0. So a equals 1. Alright, so we've got a, b, and c. Let's put them all back into our integral up here and finish it off. So a we found was 1. B we found was 2. And C we found was -1. And now we can just integrate each term separately. The integral of 1 over x minus 1 will be ln of x minus 1. This one, let's be careful, this one's not going to involve natural log because this is something of the form 1 over u squared, which is really the integral of u to the -2. So the integral of u to the -2 will be -1 over u. Okay, so this will integrate to minus, right, because there's a minus there, 2 over x minus 1. Okay, so that's like -1 over u, right? And then here minus this one will be another natural log, ln of x plus 1. There we have it. Okay, so a bit of a process, but we can see now, you know, a lot of different steps that went into it, but we were able to split up those terms and then integrate separately. And it was much easier to integrate once we've done the partial fractions.